In this lesson, we will look at power in AC circuits. We know that the power absorbed in a DC circuit is the product of the voltage and the current. Due to the change in phase relationship between voltage and current in AC circuits containing inductance and/or capacitance, the actual power absorbed is not necessarily the same as the power apparently supplied. To see the effects of resistance, inductance, and capacitance on power, we will examine them separately. And then we will look at a practical circuit having a combination of all three. In a purely resistive AC circuit, the instantaneous power value is found by multiplying the instantaneous values of current and voltage. If this process is carried out over a full cycle, it will give the power waveform shown on the screen. You will notice that the power waveform is always positive. This is because the voltage and current are in phase. So in the negative half cycle, both the voltage and the current are negative, and two negatives multiplied together produce a positive. The frequency of the power waveform is twice that of the voltage and current. The average value of this power is known as the true power, real power, or wattful power, and it is the product of the root mean squared current and voltage. It is measured in watts or kilowatts, and it represents the work being done to rotate the generator. Here we see a purely inductive circuit, where the current lags the voltage by 90 degrees. As in the resistive circuit, by plotting instantaneous values of current multiplied by voltage, we can obtain the waveform of instantaneous power. Again, the frequency of the power waveform is double that of the voltage and current. However, this time half of the wave is positive and half negative. This is because whenever the voltage and current are on opposite sides of zero, we have a positive multiplied by a negative, which gives a negative. The positive areas represent power given to the circuit to generate the magnetic field, and the negative, power returned by the back EMF. Power produced in this way is called reactive power, and is the product of a voltage and current which are 90 degrees out of phase. The units of reactive power are volt-amps reactive, or, for higher amounts, kilovolt-amps reactive. In a circuit that contains only inductance, the positive and negative portions of power cancel each other out, and the true power is zero. Power in a purely capacitive circuit is very similar to that in an inductive circuit, because the current is also out of phase with the voltage. But this time the current leads the voltage by 90 degrees. Once again, the positive power is equal to the negative power. Thus no true power is absorbed. The circuit power is again all reactive power. A practical AC circuit will always have some resistance and some inductance. The amounts of each will depend on the construction of that circuit. The circuit may also have capacitance if capacitors are fitted. All AC circuits therefore have both resistance and reactance. These will produce true and reactive power respectively. The total power being felt in the circuit will be the vector sum of the true power and the reactive power. This power is known as apparent power. It is also sometimes referred to as theoretical power or rated power. Irrespective of their phase relationship, apparent power can be calculated by multiplying the RMS voltage by the RMS current. It is measured in volt-amps or kilovolt-amps. We can use a similar vector diagram to the one that we used to calculate impedance to work out a circuit's apparent power. In the power vector diagram, we have true power along the baseline, and since in a reactive circuit the current is 90 degrees out of phase with the voltage, we have reactive power at 90 degrees to it. As we said, the apparent power in the circuit is the vector sum of the true and reactive powers. The phase angle, which is the angle by which the current leads or lags the voltage, is the angle between the true and apparent power lines. The relationship between true and apparent power is an important one. It is expressed as a power factor, or PF. The power factor is the true power divided by the apparent power. As you can see from the vector diagram, this is the cosine of the phase angle. In a theoretical purely resistive circuit, the phase angle is 0 degrees. The true power is equal to the apparent power, so the power factor is 1. This is good, as all of the power in the circuit is being used to do useful work. In a purely reactive circuit, the phase angle is 90 degrees, the power factor is 0, and no useful work is being done. Circuit designers attempt to maintain the power factor as close to 1 as possible. That is the end of the lesson. Here is a summary of the main points. The power used to overcome resistance is known as real power, true power, or wattful power. It is measured in watts or kilowatts. It represents the work being done to drive the shaft of the generator. Power produced in a purely inductive and/or capacitive circuit is known as reactive power. It is measured in voltamps reactive or kilovoltamps reactive. The total power being felt in a circuit containing both resistance and reactance is the vector sum of the real and reactive power, and is known as apparent power. It is measured in voltamps or kilovoltamps. The power factor is the true power divided by the apparent power, or the cosine of the phase angle. In a purely resistive circuit, the phase angle is 0 degrees, the true power is equal to the apparent power, and the power factor is 1. In a purely reactive circuit, the phase angle is 90 degrees, and the power factor is 0.